Today, we're going to talk about one of the most fundamental skills for anyone who works with data, exploratory data analysis. We've all been there, right? You're handed this new data set, thousands of rows, dozens of columns, and the first question is always, where do I even start? The temptation is to just jump right in and start building a model, but that's a mistake. See, the very first step isn't about building anything. It's about changing your mindset. You have to think like a detective arriving at a crime scene. And by the end of this, you'll understand exactly how to do that investigation using a process called Exploratory Data Analysis, or EDA for short. So what is EDA? Well, at its core, it's the process of just getting to know your data. It's this open-ended investigation where you use basic stats and, maybe more importantly, visuals to really see what's going on. You're looking for the big picture, the oddities, the story that's hidden in the numbers. Now, it's really important to understand the difference between these two mindsets. On the right, you have what most people think of as data analysis. You have a hypothesis, and you want to test it. But EDA, that's what's on the left. It's the discovery phase. You're not trying to get answers just yet. You're trying to figure out what the right questions are to begin with. And that's the key idea. EDA is the step you take before you have a theory. It's all about letting the data speak for itself without you imposing your own assumptions on it first. So, as this data detective, what are you trying to do? Well, first you check the quality of your evidence. Is the data clean? Anything missing? Then you look at each clue, each variable in your data set, all on its own. After that, you start looking for connections between the clues. And finally, all of this work gives you solid leads for your main investigation, which for us is usually building a machine learning model. Okay, let's open up the detective's toolkit. The first job is always to examine each piece of evidence by itself. The technical term for this is univariate analysis. Uni means one, and variate means variable. So pretty straightforward. We're just looking at one variable at a time. And you do this in two really simple steps. First, you calculate some basic numbers, the mean, the median, min, max. And second, you draw a picture. You visualize the data's shape, maybe with a quick histogram. Let's make this real. Here's a table from a data set about breast cancer patient survival. We're looking at a variable called positive axillary nodes. Now, notice something interesting here. The mean, or average, is about 4, but the median, the middle value, is only 1. A good detective sees that and immediately knows something's up. That big difference is a clue that a few extreme values are pulling the average up. And then boom, the visualization makes it obvious. This bar chart shows that most patients have very few positive nodes, between 0 and 4. But there are a few patients with a lot of them, and those are the outliers that were skewing our average. That's a huge insight, and we got it just by looking at a single variable. All right, so once we've looked at each clue by itself, the natural next step is to see how they relate to each other. And this is called bivariate analysis. Bi, of course, means two, so now we're looking at variables in pairs, hunting for correlations and hidden patterns. This is where we can start asking really interesting questions, like, does our main clue, the number of positive nodes, actually have anything to do with the outcome we care about, in this case, patient survival? And look at what we find. When we split the data into two groups, those who survived and those who didn't, a very clear pattern jumps out. The patients who died had, on average, significantly more positive nodes. Now, our clue isn't just a curiosity. It looks like a really strong signal. We can even put a number to it. Our investigation shows that for patients with 4 or fewer of these nodes, the survival rate was about 85%. That is a powerful, concrete insight that we dug up through simple EDA. So how does all this detective work actually help us when we're building machine learning systems? Why should you care? Well, EDA is absolutely critical. It's how you identify the most important features for your model. It's how you spot the errors or outliers that could completely mislead your algorithm. It can even help you decide which type of model to use. Put simply, skipping EDA is the fastest way to build an unreliable or just plain wrong model. In our little investigation, EDA did its job perfectly. It basically pointed a giant flashing arrow at the positive axillary nodes variable and said, hey, pay attention to this. This is important if you want to predict survival. So if you only take one thing away, let it be this. EDA is the process that turns a confusing mess of raw data into a coherent story you can actually understand. And the key takeaway? Never, ever build a model on data you haven't looked at first. Your assumptions are not evidence. You have to let the data provide the evidence.